Going to continue talking about acids and bases, but first let's talk about strong bases. Strong bases occur when you have complete dissociation of the base. So whenever we had sodium hydroxide, it completely dissociates into sodium ion and the hydroxide ion. The strength of the base is based on the percent of units dissociated, not the number of hydroxide ions produced. So if this acid breaks apart completely and there's none, or sorry, if this base breaks apart completely and there's no sodium hydroxide left in solution, you only have sodium ions and hydroxide ions, then that is considered a strong base. The strongest bases contain hydroxide ions and are from groups 1 and 2, so the alkali metals and the alkaline earth metal hydroxides. Strong acids, you can't just look at the periodic table and say these elements make a strong acid. That's a little bit more complex than the strong bases. Strong acids also completely dissociate in water. So if we have hydrochloric acid, for example, if it's in solution, you're only going to find hydrogen ions and chloride ions. It completely breaks apart. So here you have hydrochloric acid plus water. And you have your hydronium ion and your chloride ion. A 1 molar solution contains 1 molar solution of, it contains 1 molar solution of hydronium ions and a 1 molar solution of chloride ions. If we had a 2 molar solution of hydrochloric acid, we'd have 2 molar solution of hydronium ions and 2 molar solution of chloride ions. Strength is not a concentration for either acids or bases. So if you say this is a strong acid, it doesn't mean that it's highly concentrated. What it means is it completely dissociates. The strength of an acid or a base only refers to whether or not it completely dissociates. So here we have our strong acids and our strong bases. Strong bases, they're group 1 or 2 elements paired with hydroxide. Those are your strong bases. Your strong acids are these. They're your perchloric acid, sulfuric acid, which is part of acid rain, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid, which is again another constituent of acid rain. Now, in weak acids, there's very little dissociation of the acids into ions in water. Same thing with weak bases. Very little dissociation of the base into ions in water. The major dissolved component is the unionized acid or base. And although most acids and bases are classified as weak, their behavior is significant because most acid-base reactions in living systems occur between weak acid and base interactions. So the coiling of your DNA, that happens because of weak acid and weak base interactions. And that coiling of your DNA is really important. The observed range of possible hydroxide or hydronium ion concentration span from 10 to the negative 14th molar to 1 molar. To make this scale possible, to use the pH scale, which is the potential hydrogen scale. That's what pH stands for, the potential hydrogen scale. And it was invented by S.P.L. Sorensen. Because, of course, we know that acids dissociate to form the hydrogen ion, which then reacts with water to form the hydronium ion. So here we have the potential hydrogen ion. It is what pH is measuring. pH is a mathematical scale in which the concentration of hydronium ions in a solution is expressed as a number from 0 to 14. The pH value is the number of the exponent. So if we have 10 to the negative 11th, the pH value is 11. If we have 10 to the negative 1, the pH would be 1. 10 to the negative 2, the pH is 2. So you're just going off the exponent. So which base is considered strong because it completely dissociates in water? We look and we say, well, groups 1 and 2. So this one is actually has multiple. It's both B and C because groups 1 and 2 completely dissociate in water. So it's B and C. I want you to try these others on your own and then come back and check on them. So here we have what is a characteristic of weak acids and weak bases? Do they A, highly reactive with metals, B, completely ionize in water, C, they partially ionize in water, or D, they are not electrolytes? So let's look at this. We know acids and bases, whether they're weak or strong, will ionize in water. And if they ionize, they're going to conduct electricity. So it's not this. They aren't highly reactive with metals. Now, strong bases and acids completely ionize in water. So that means your answer is C. They only partially ionize in water. They don't break apart completely. 3, which of the following is a strong acid? If you look on that previous chart, you'll see that hydrochloric acid is a strong acid. Carbonic acid is a weak acid. Hydrofluoric acid is a weak acid. And acetic acid is your vinegar. It's a weak acid as well. The hydroxide ion concentrations and hydronium ion concentrations are multiplied together to form 10 to the negative 14th. So if you have a pH of 3, so if your pH is 3, then the hydronium ion concentration is negative 3. And the hydroxide concentration is 10 to the negative 11th. Together, that is 10 to the negative 14th, because whenever you are multiplying exponents, they're added together. When you're dividing exponents, they're subtracted. The total pH, remember, always has to be 14. If you're multiplying 10 to the negative 3rd times 10 to the negative 11th, that gives you 10 to the negative 14. Remember, these exponents are added when you're multiplying. When you're subtracting or when you're dividing, they're subtracted. Here are some examples of the pH scale and some common items that have this pH. So we have three different sections of the pH scale. We have acids, which is everything below 7. We have neutral, which is 7. And we have basic here. So this is acidic, and this is basic, and this is neutral. Now it's neutral because at the pH of 7, your hydrogen ion concentration is 10 to the negative 7th, and your hydroxide ion concentration is 10 to the negative 7th. So they're equal. If they're equal, then they cancel each other out and they're neutral. Pure water. This isn't our tap water, but this is pure water. So our distilled water that has no impurities in it whatsoever. pH of 7 is neutral. Every unit, because remember we're dealing with exponents here. So 10 to the negative 1, 10 to the negative 2. This is 0.1, 0.01. Every unit of increase or decrease, because remember this is your pH of 1, pH of 2, etc. You can see that it's a factor of 10. So that changes by a factor of 10 here. Between 1 then and 3, if this is 10 to the negative 3, this would be 0.001, which is a pH of 3. You can see that it's hugely different. It's 10 here, so it's a difference of 10 here, and a difference of 10 here. So 10 times 10. So it's a factor of 300 or of 100 difference between a 3 and a 1. So the solution, if we're looking at a pH of 3 versus a pH of 4, pH of 3 has 10 times the concentration of hydronium ions than a pH of 4 does. So each time you move up, you're multiplying by 10 in concentration. So you could see the vast difference of concentrations. And that's why, again, we simplified it where we're looking at the exponents instead of looking at these values. We just use those exponents as our pH values. Now in neutral solutions, the concentrations of hydroxide ions and hydronium ions are equal, as is illustrated right here. And that's why it's considered neutral. Now above 7, we have the concentration of hydronium ions that it decreases by a factor of 10, while the concentration of hydroxide ions increases by a factor of 10. Because, of course, the exponents of, remember, if your hydroxide ion is 10 to the negative third, your hydroxide ion would have 10 to the negative 11. So as your hydronium ion concentration decreases, your hydroxide ion concentration will increase. So as we go above 7, the hydroxide ion concentration is much larger than your hydronium ion concentration. pH is extremely important in our bodies and in the environment. We talked about some adverse effects of acid rain because it's changing the pH. We test the pH of the water in swimming pools. We use different indicators for testing pH. In swimming pools, if the pH isn't correct, you can damage your skin. You might not kill all of the bad organisms that are in the pool water, which would result in us getting sick. So you must use proper care if you do have a swimming pool. It's really, really important. Okay, let's look at these practice questions. I want you to try these and then come back and check your answers. If we have a solution that has a hydrogen ion concentration of 1 times 10 to the negative fourth, what's its pH? We're looking at hydrogen ion concentration. So the pH is 4, which is B. If a solution has a hydrogen ion concentration of 10 to the negative 8th, what's the hydroxide concentration? So if our pH is 8, our POH, which is our hydrogen ion concentration, has to be 14 minus 6, or 14 minus 8, which is 6. So our POH would be 6. If we're looking at the concentration, that needs to be in exponent form. So that's going to be 1 times 10 to the negative 6. How many times more acidic is a solution with a pH of 3 compared to a solution with a pH of 6? Okay, remember, for each digit that you change is a multiplication of 10. So from here, 3 to 4, that's a factor of 10. From 4 to 5, that's a factor of 10. From 5 to 6, that's a factor of 10. So it's 10 times 10 times 10, which is 1,000. If you have questions about these, please don't hesitate to reach out. Now let's look. The Bronsted-Lowry definition of an acid is that the acid donates a hydrogen, a base accepts a hydrogen in a chemical reaction. So the way I remember it, again, I do little things to help me remember, is bad. Bronsted, acid, donor. So if I remember bad, Bronsted acid donor, the acid donates the hydrogen ion. The base accepts a hydrogen ion. So knowing that, Bronsted acid donor, which would be the acid and which would be the base in this reaction? Well, we have hydrochloric acid, we have ammonia, we have ammonium chloride here. So what happened? What donated? Well, we have NH3 on the reactant side and NH4 on the product side. So it's NH3, hydrochloric acid donated its hydrogen to ammonium to ammonia there. It's important to remember that water can act as either an acid or base based on Bronsted definition. Oh, so if this is your acid donating, then this would be your base accepting. I forgot to let you know that. So if we're looking at a weak acid plus a strong base, because you do have that reaction, you do have those reactions, you're always going to get a salt and water. But of course, salt and water are always the products in acid-base reactions and neutralization reactions. You always get a salt and water. It might still be acidic. The result, the products might be still acidic or still basic, but you're always going to have a salt and water. Here's an example. You have your acetic acid plus your sodium hydroxide, and this gives you sodium acetate plus water. See, you have your salt and your water still. Now, acetic acid is a weak acid. Sodium hydroxide is a very strong base. It's going to dissociate completely. Your weak acid won't dissociate completely. So if I were to draw this to show the dissociation, I have my acetic acid, which doesn't dissociate completely. So it's still going to have some acetic acid in the reaction, in solution, plus sodium ion, which dissociates completely, and your hydroxide ion, because your sodium hydroxide dissociates completely. And then salts break completely apart in solution. And then you have your water molecules. So if I did the net ionic equation, which is where I say, well, I'm going to mark out the ions that are on both sides because they cancel each other out. My net ionic equation is my acetic acid plus hydroxide ions gives me my acetate ion plus water. Seeing that hydroxide ion right here, seeing this indicates that the final pH is going to be basic because it's a strong base. I'm going to have extra hydroxide ions floating around. I'm not going to have extra hydronium ions floating around. Now, buffers are solutions that resist changes in pH when moderate amounts of acids or bases are added. And they contain ions or molecules that react with hydroxide or hydrogen ions when these ions are introduced into solution. Buffers are basically shock absorbers. So you can add more acid or base and they'll react to keep it more at the same pH that it was. So it's like, all right, yes, you can add more, and I'll adjust the system, but they only have a certain capacity. They can only handle so much before you have a significant pH change. Now, the most common buffers consist of approximately equal molar amounts of weak acid and a salt of the weak base. So you need approximately equal molar amounts of weak acids and the salt of its conjugate base. If we dissolved, this is just an example, if we dissolve 1 mole of acetic acid, and 1 mole of sodium acetate, which is its conjugate base, the salt of its base, and water, you're going to have an acetate buffer because it's equal molar amounts, weak acid and a salt of its conjugate base. These are the common ones. So here's what it looks like. We have our acetic acid plus water, and we have our acetate ion plus hydronium ions. So this is the net ionic equation. We're going to add some, oh, there we go. We are going to add a strong acid, like hydrochloric acid. If we add hydrochloric acid, we're going to add hydronium ions into the buffer. If we add hydronium ions, it'll react with the acetate ion. So to form here, if we add hydrochloric acid right here, we're basically adding more hydronium ions. These hydronium ions will react with the acetate ions right here to form a weak acid, your acetic acid. Weak acids won't change the pH that much. If you add a strong base, what you're going to do is that strong base, of course, will break apart into ions, and it'll react with the acetic acid that's already in solution and form the acetate ion. So it's not going to change the pH as much because you're pairing those extra ions you're adding, whether it be the hydronium ions or the hydroxide ions, you're pairing it with either the acetic acid or the acetate ions, and you're making water plus a weak acid, which won't affect the pH as much, or water and an acetate ion. Again, this is how buffers work. It doesn't prevent any change at all in the pH, but it makes the addition of those hydroxide ions or hydrogen ions less severe. So you're not going to have a huge change in pH. It'll just be a slight change in pH. Now, our blood system has a buffer system as well. We have carbon dioxide dissolved in our blood because, of course, we inhale oxygen and then we exhale oxygen as our waste. And our blood carries the oxygenated blood and the deoxygenated blood back to our heart and our lungs. So the blood is able to maintain a pH of 7.4 due to a carbon dioxide buffer system. Now, the level of carbon dioxide in the blood is determined by the lungs. Your body yawns to get rid of excess carbon dioxide. And every time I say yawn, it makes me want to yawn, so I apologize. If you're hyperventilating, you actually are breathing out too much carbon dioxide, and that's an issue. That's why they say, here's a paper bag, breathe into the paper bag. Because you need to reestablish that balance of carbon dioxide to oxygen. A natural buffer is calcium carbonate, and that's also known as limestone. Limestone-rich areas help to offset the effects of acid rain through the neutralization process. Antacids are made from calcium carbonate as well, and they help neutralize the excess acid in your stomach. So if you know that you have too much acid, you could take some Tums, which is calcium carbonate, and get that neutralization process going. You can also drink some milk with it, which is slightly basic. There are two types of antacids. You have one, the hydroxide antacids, and these have a very low solubility in water, so they won't react until they reach your stomachs. So if you take a hydroxide antacid, you don't have to worry about it starting to bubble and foam in your mouth. You can swallow it and it won't react until it gets to your stomach. Now, your carbonate antacids, they'll react with acids to produce carbon dioxide and water. And if you take those, you're going to be burping more because you've got to get out that excess carbon dioxide. We are going to stop there for now, and I'll see you next.